All right, let's continue. Is my mic open? Okay, good. Uh, so we stopped here. The gravitational acceleration of Jupiter is said to be 25.2 meters per second squared. And we're asked to look for the mass and the weight of the bread on Jupiter. I think we're talking about the same bread, so the mass is on Jupiter is still going to be the same thing. So it's that. And for the weight, uh, we'll use the formula W is equal to mg. Mass is going to be 0.54082 kilograms. And the gravitational acceleration is 25.2 meters per second squared. So for the weight, it's 13.62866 newtons. Kilograms times meter per second squared is newtons. Let's see if the answer is correct. Okay, good. Let's calculate how much force a table has to apply to a 50 kilogram TV that is placed on it. Okay, so the weight is 50 kilograms. If we're supposed to look for force, I suppose we use this formula. But the question is how. Let's see what the answer key says about it. Okay, we still use W is equal to mg. And this is the table. So how much force? That's what we're looking for. The weight is 50 kilograms. Sorry, yeah. And the mass is missing. Gravity is 9.8 meters per second squared. So if you want to look for the actual mass of the television, it's going to be 50 over 9.8. That is equal to 5.10204. The mass is kilograms, I think. Is it? Yeah. Wait, no. No. Something's wrong here. 50 kilograms is actually the mass of the television itself. So the weight is missing. This is so messed up. So that's a lesson for everyone. Reading the problem is very crucial. Although your solution is going to be correct, like how you use this formula and this and that. If you interpret the values wrongly, then you're set for disaster. Gravitational acceleration is 9.8. So 50 times 9.8, that is 490. So yeah, the force is supposed to be 490. In order to make this 0 newtons, the normal force should also be 490 newtons, I suppose. What does this thing say? Okay, so normal force, weight, yeah. I think it makes sense even if you don't write this there. Mass is 50 kilograms, just for reference. And yeah, we don't have to put this too. But then yeah, for reference only. Fn minus W, that's supposed to be 0n. If it's not 0, it's either going up or it's falling, which is not the case here. So it's 0 newtons. The red and blue team are having a tug of war. After 2 minutes, the flag has not budged a bit. The red team has 12 people pulling with 200 newtons of force. Let's say this is red, this is blue. So red has 200 newtons of force, blue has 10 people. How hard are each of them pulling? Okay, so we don't know that value. Let's see if we can calculate for it. Perhaps ratio and proportion. I hope this works. 10 people. And then we have how many newtons in that case? If 12 is to 200, 200 divided by 12 is 50 over 3. So 200 times 50 over 3 is equal to, wait, no. This is supposed to be 200 divided 50 divided by 50 over 3. That's 12. So x divided by 50 over 3, or just simply 3 over 50, is equal to 10. Are we even close? That's just weird. Okay. Sorry. I'm not reading the instructions properly again. All this is wrong. We have to 12, so each person in the red team has 200 newtons of force. So 200 times 12 is 2,400. So if it's 10 people, then we have 2,000 newtons. Wait, no. It says that the flag has not budged a bit, so you can say that the blue team is stronger. Although they only have 10 people, their share of pull is considerably stronger compared to each individual from the red team. So 2,400 divided by 10 is 240. So I suppose each person from the blue team has 240 newtons. Basically 40 more than 200 that's from the red team. So in order to compensate, so equal strength and neglect the weight of the rope. Okay, so we neglect the weight. We don't write it in the free body diagram. The force is 240 newtons, so we got it. Okay, so my solution is somehow similar, although they're written in a different way. uh, based on the free body diagram, we have T1 minus T2 is equal to 0 newtons. This is T1, 2,400 newtons. This is T2, it's also 2,400 newtons. So yeah, you find the difference between the two values, you find 0. So yeah, 214 newtons. We got the answer anyways. So a piece of block with a half kilogram of mass was pushed with an acceleration of 20 meters per second squared. So FA is equal to 20 meters per second squared. Not sure if this is supposed to be in newtons, but yeah, wait, no. The applied force is missing, but then the acceleration is given. Okay, I suppose this is where we use the F is equal to ma formula. So force, which is the one we're looking for, the applied force, is equal to the mass, which is 0.5 kilograms. We don't have to convert to any other unit since the SI unit for mass is kilograms. And the acceleration is meters per second squared. That's also the SI unit for acceleration, ideally. So 0.5 times 20. That is equal to 10. In other words, 20 times 1/2. Of course, the unit of FA will be newtons. So what saved me from getting the wrong answer a while ago was doubting the idea that acceleration is the applied force. What made me think that they're not the same? Well, the four forces in the free body diagram, their unit is Newton. If it's just meter over second squared, then that's not Newton. So the value cannot be, can be suspected to not be the actual force value. So we have 10 newtons. Is that the same answer? Oh yes, yeah, we found it. Note the acceleration here has no friction involved. Okay. Yeah, best note that also. Alright, so for letter B, with the same system, a 2 Newton of friction was applied to the system. Okay, so let's draw the same thing. I'll just copy paste. 2 newtons, that is gonna be where? This is the frictional force. It's equal to 2 newtons. So what is the net force? So the net force, if you want to look for it, we always write this one. So summation of Fx is equal to Fa minus the friction. Fa is, we already know it's 10. So remove the question mark there. It's 10 newtons, and then the friction is said to be 2 newtons. Therefore, the net force is going to be 8 newtons. So yeah, answer is 8. We got it right. How about the weight of the object? So yeah, let's duplicate the same diagram. We this time place W, the weight. So what formula do we use? W is equal to mg, such that the weight is missing. The mass, we know it's 0.5 kilograms, and the gravitational acceleration is 9.8 meters per second squared. So 0.5 times 9.8 is equal to what? 4.9. And then the unit for weight is, I know it's newtons, but why is it meters per second? I'll just stick with newtons. I won't write meters per second. Oh wait, yeah, it's already said there. I think this is a typo. Anyways, for letter D, what is the normal force applied on the object? You know what? I'll just write it in a new page. Okay, so the normal force, what are we talking about again? It's a piece of block that's being pushed. So the surface is somewhere here. Naturally, now that we know what the weight value is, which is 4.9 newtons, since the object isn't falling or isn't flying, being pulled from above, it's just stable. The normal force is supposed to be equal to the weight. If it's just lying still on the surface. So F of n is equal to 4.9 newtons. Okay, how about for letter E? The kinetic frictional coefficient. Fancy term. I know it's abbreviated as mu. I'm just not sure what the two values are so that you could find it. I know you divide those two. So formula for friction. There, I knew it. We had to divide two things. We derived the formula from F is equal to UN. So what is the friction? I suppose this is the frictional force and the other one is the normal force. Is it? Let's find out. Okay, so the frictional force is two newtons. How about the normal force? 4.9. I wonder what's the answer gonna be. 2 divided by 4.9, that is equal to 0.4082. Nice. So what is the unit for frictional coefficient? We are dividing Newton by Newton, so I suppose there's no unit for that. Let's search for it first, just to be sure. Okay, so there are no units for frictional coefficient. So we just write the number. It's similar to writing pH. pH has no units. So what is the new acceleration of the system? Before we proceed though, let's start writing our formulas. So okay, so we have F is equal to ma. I think this is Newton's second law of acceleration. And we do have the weight is equal to mg, mass times the gravity. We also know the formula for friction. Friction is fun, like literally fun. And then from there, you can derive the idea that the frictional coefficient is equal to the frictional force divided by the Newton, the normal force, basically. So what is the new acceleration? I suppose we use F equal to ma. I'm thinking that the force here is supposed to be the FA, the applied force, for some reason. It kind of makes sense, I think, since applied force is the force that is involved when the object is moving. So it's somehow related to acceleration if you think about it. Unlike other kinds of forces. Okay, the app is lagging. Never mind, it's here now. So acceleration is 10 over 0.5. What is that equal to? That is equal to 20. 20 meters per second squared. Okay, we have a different answer. What would make the answer 16? Let's have some experimentation. Alright, I give up. What does the answer key say? Okay. We are supposed to consider the frictional force also. So 10 newtons minus 2 newtons, that's going to be 8. So 8 divided by 0.5 is 16. Alright. Makes sense. Let's move to the last question. After this, I suppose my review for physics is finished. We'll move on to biology for the next videos. It's gonna be pretty fun, I suppose. I hope so. Anyways, so a 1-ton cargo is falling from the sky. If there is an air resistance of 1000 newtons, I suppose air resistance corresponds to the force going up. So 1000 newtons is equal to AR. Instead of writing normal force or T for tension or density or tensile strength, we write air resistance as it is. And what will be the net force of the system? We do not ignore air resistance, we consider it, and I suppose there are only two forces at this point. There's no going left or right, even though realistically it may move left to right for some reason. The weight, we don't know what it is. Oh, we actually do know the weight, or the mass in particular. That is 1000 kilograms. Let's compute for the weight of the object. So W is equal to mg. Weight is missing. We know the mass, which is naturally 1000 kilograms, and the gravity is 9.8 meters per second squared. So the weight is 9,800. I told you it's a different value when it comes to weight. Now, we have to compute for the net force concerning Fy. So we have air resistance minus the weight. Air resistance is said to be 1000 newtons and the weight is 9800 newtons. The weight is bigger, so naturally we should expect for the object to actually land on the ground. And the land will be quite violent since the weight is really big. And the longer time it stays midair, it's able to muster a lot more kinetic energy, and that translates to a lot more final velocity going down, the vertical velocity, VFY. So I suppose that is the net force of the system. Okay, something's wrong. Yeah, we did find the summation of Fy. We also know the weight. Yeah, I should write the mass beside the box just to be as close to the professor's solution. Where is the 1.7? Well, this is everything, according to the answer key. Well, we did it, I guess. Negative means going down. So, summation of Fx or Fy is gonna always relate to the net force. So if we have to look for the net force, the moment you read this term, always know that it's either summation of Fx or summation Fy. That's it. We're done. I hope I score as high as possible in my exam. So that's it for this video. Thanks for watching.